Okay, my plan for today, I didn't want to get too far ahead of schedule. So today was scheduled to be the experimental design, which we can finish up. Um, it won't take the whole time. Quite frankly, all I want to do is review yesterday's material fairly quickly, walk through this paper, which I think is a good tutorial. This is, no, not this one, sorry. This one's okay, it's an example, but I'll walk through this paper. But this guy, Experimental Design for Simulation, and these papers are available to you on the Canvas site. So we'll walk through these, and then that'll leave time. I want to look at your writing if you have any for the next deliverable. And if you don't, then just make sure we're understanding what should be included in the in the background section, and go through if you have any questions or specific ideas. And then after that one-on-one, we're all set. I suspect, and actually it wouldn't bother me if we're done by about 10, because I've got a meeting that I want to go to also. All right, so that's the plan. So the basics of the experiment design, and you can see how there's maybe a chicken and egg problem. You start out, usually the sequence that people start out with simulation, or with an experiment, I should say, is they do start out with the research question and then with a hypothesis, which then implies that you have an idea of what variables you need to play with, right? Normally, so I want to study the effect of X on Y. Oh, okay, you just named two variables. Then you get into building the model, building the simulation, and your research questions and the description of those variables are going to drive what you choose to include and not include in your model, and to what degree of fidelity you need to build your model to. So everybody's doing UAVs for years now. Are they massless points in space, or are they full-figured dynamics, stability, system feedback kind of physical models? It depends on what your research question is. Once you create the model and the simulation, now you're back to experiment design, but that echoes back to your original research question. How am I going to conduct the experiment? So it's a situation where you kind of need to, well, you definitely need to know where you're going before you get there, but you're kind of doing a loop here. And you may find when you get down to your experiment design that, oh, I forgot this particular aspect that I think might be important. Therefore, I need to go back and revise my model, whatever. Even though your research question says I want to study the effect of X on Y, that doesn't mean those are the only two things that you need to model. You then need to put your whatever you're studying, whatever the model is, in some kind of an environment. The environment has its own variables, right? So, we went through our list of independent, dependent, extraneous, confounding, and controlled. A lot of things may be extraneous in the context that they may not have contributions to different outcomes if they're varied, but they're necessary just for the model to work, for the simulation to work. So if you're doing a traffic study and you're doing a long straight road, you may need to have a long enough road for some effects to show up. A short road won't work, right? So you may need a long enough road. Well, the length of that road probably isn't going to be an interesting experimental variable, in the sense of, do you get radically different behaviors having a 20-mile segment versus a 19-mile segment or something like that. Okay, so that's the process. Now, if we look at this paper, he starts to talk about experimental design. And let's ask some of these questions. I'm going to make this bigger, particularly for the recording. These are the kinds of questions, right? What model configuration should you run? Okay, so what does that mean? You have a model. You may be setting certain attributes of that model to certain values. Is the agent aggressive? Is the agent passive? Is the agent, making the same decisions all the time, et cetera, et cetera? How long should the runs be? Now that depends again on what your research question is. So how long should the run be to map a room? Well, until you've mapped the room. Or if it's absolutely failing and it will never map the room, you need to have some arbitrary cutoff point. As opposed to fuzzy cognitive maps, how long should you run? You need to run long enough to find a pattern. The pattern may be that everything converges to the static situation. Highly unlikely. It's going to be more likely that it converges to some static situation within some upper and lower boundary for each value of the node. We could call that convergence. But it also may be, as we said yesterday, chaotic, or it could be some kind of sinusoidal behavior. How many runs should you make? This is the kind of question that they try to answer when you took MA 412 statistics. What is a statistically significant number of samples? And what was it? There's a Z value, right, that you can compute. What's the other one when you have less than 30 samples? Was it R or P? No, it wasn't P. It was B. I think it was an R value, an R factor. Anyway, the statistics become different for a relatively small number of samples and a relatively large. If you are very clever about how you build your software, you can build your software where you're telling it, hey, run this experiment, but now put it in a loop. Run it n times. And if you do that trick and you're able to aggregate the data or save the data in some fashion, then it's really easy to just get a bunch of runs. One of the blessings and problems with the computer simulation is you can just get so much data so fast, but then that's the blessing. And then the curse is you have so much data, and now you have to figure out how to turn that data into information, right? How do you process it? And there we go. How should you interpret and analyze the output? And you can argue about that with people for a very long time. What does this data mean? That's a very difficult thing. Oh, now they can see my screen. Oh, Alex is on. Okay. So analyzing and interpreting the output, it's the kind of thing that you don't think would be an issue until you run into the issue. What did it mean that when we did X, Y occurred? Is that causation? Is that just some indirect effect, something else? And then what's the most efficient way to make the runs? This gets down to a couple things. Number one, just the experiment design. We talked yesterday, if you did a full factorial suite of runs, you may have an infeasible number of runs. 10 variables, two values each, 1,024 scenarios. 1,024 scenarios, maybe you need to run each of them 50 times in order to get statistically significant results. Now you're looking at 50,000 runs. It adds up fast. So what's the most efficient way? The first level of efficiency is to do the experimental design in such a way that you feel like you've got pretty good coverage of the situation without necessarily having the full factorial, the full suite. And that's what this paper is talking about next, is what are some ways that people try to cover that. But another way to think of it, and it's not necessarily as obvious with computer simulations when we talk about efficiency, is about the sequencing. You can imagine if you had a simulation that had physical components and you had to reset the physical components a particular way for a particular scenario, it may be that if you have I don't know, the door is locked in this scenario. Okay, maybe we should run all the scenarios where the door is locked in a sequence rather than constantly locking and unlocking the door. Or we're going to have some obstacle in the room for these scenarios, but not in some other scenarios. Well, you don't want to keep hauling the obstacle in and out of the space. So there may be situations where just the setup time is made more efficient because you're taking advantage of doing simulation sequences where the setup time has less of a change from one version to another. With large complex simulation systems, it can be difficult. And again, unfortunately, we don't get to experience in the academic environment very often true complexity like you get out into the real world. So if you have a really complex experimental system, simulation system out in the real world, generally it's a system of systems that's made up of a bunch of components. And so this whole thing about being efficient can make sense. The whole idea of interpreting the data can be tough. A lot of this stuff is about training. So in training, what kind of results are people interested in? They want to make sure that the person who was being trained learned behaviors and skills that are applicable to the real world. And you want to make sure that the training was occurring efficiently. You want to get someone to a certain skill set basically as quickly as you can. Which means, how do you interpret and analyze the results? So if we have these flight simulators down here, and we should tour that facility. I'll try to set up a tour of that. So have you been in there?
I built them.
You built those, or ones like them?
The little small testing room. I was one of the people who was.
Which one though? Where?
One of the flights.
Okay.
Yeah. I helped. Didn't help too much with the main construction, but I helped optimize their systems.
Okay. Yeah. We should go. They've got also just a remarkable speech to text interface, so the human pilots can interact with virtual agents. So let me see if I can set that up before the end of the semester. But anyway, there's a lot of money, and as you know, they spent millions on that. How much better is that than, if I said the old link trainers, would anybody know what I'm talking about? the old 1930s link trainers, which was basically a tin can on a pivot, and you sat in there and they spun you around and tilted you back and forth, and they put a hood over your head, and they had a person acting as air traffic controller. How much better did those millions of dollars get? I assume better, right? Assume better, but that's the kind of thing that's hard to measure. It really is.
Well, as far as the school's funding model goes, it made it a lot easier to send. They were limited to basically taking approximately like 20 to 30 flight students per class, and now they can bump it up to about 50.
Right. So, well, and not only is that good from a throughput standpoint, but think of it from a revenue standpoint.
Well, that's what
right.
Yeah.
Yeah. So, but that didn't talk to the quality of the training. It talked to the volume of the training, right? I'm presuming that these more sophisticated systems actually provide a better training experience, but you should always ask the question, to what degree is it better? It's effectively as close as you can get to being in the real airplane, I would imagine, because
double the first time walk successful.
Oh yeah, there you go. And those are measurements, right? Those are real world measurements. Yeah.
So I'd say that's basically made it where every student essentially went through the first time going out there and doing their walk arounds and passed. Instead of a lot of them having to go twice.
Right. And that's the kind of data that you would collect in something like that. Okay. again, what's the purpose? In software engineering, we talk a lot about requirements and try to teach the software engineers, the students, if it's not a requirement, don't do it. And so that's what is the purpose of this experiment, right? So if the purpose of the experiment is to do X, is to investigate research question X, build your simulation, build your model around that research question. Now, it may be that you are building a tool set larger than the specific research question for other reasons, marketing reasons, right? Or you're trying to develop a product that you hope to get other revenue from. That would be a different reason than just what's the purpose of this specific experiment, and you may expand the capabilities of the model or the simulation at that time. But generally, these things tend to be handcrafted, used within this space. It's remarkably frustrating for people that, look, I did this model and simulation experiment 2 years ago. Somebody else wants to use it, but it turns out they can't because everything I did was just so handcrafted to the research question that it's just better for them to start over from scratch or use very little of what I did for a foundation. That's a normal experience, at least in the research world.
A lot of that, though, at least in my experience, is because they don't.
Some of it's documentation issue.
It's mostly the documentation, and also if you write things as programs within programs and then label them, instead of just calling them the thing that does a thing.
Yeah.
You'll have a lot more reusability. It's like if you have a whole entire page, but you break it down into 4 different programs that all interact with each other
Right.
in some way.
Right. Yeah, you want to, and that's a software design issue or a product design issue. You want to have modular pieces, and that's one of the goals. If you have truly modular pieces, then hopefully you get more reuse out of them. There's a whole branch of people, component-based software people that are trying to figure out how can you make that as large as possible. Python has kind of sort of achieved that in the sense that they have a lot of libraries that people can just grab and plug into their system. So anyway, random numbers. Random numbers are your friend. Generally, in a simulation system that is trying to investigate cause and effect, you will have some form of random number generation. If you didn't, you would have a deterministic system, meaning for the same initial conditions, you would always get the same output. Well, that's not generally helpful in an experimental situation because now it doesn't matter how large your sample size is, you're always getting the exact same output. And that's not how generally real world situations work. So if we go to the opera problem, you got 10 people in a room and they walk out of the room and you've seen this every day in your class, right? Or 5 times a day in class. You go to the class, you got 30 students in the class. At the end of class, they walk out of the room. Now, pay attention. How many days in the semester do they walk out of the room in the exact same sequence? Never, right? There's 30 factorial sequences that could be done. Never. So if you had a model that didn't take that into account, that kind of just banal randomness, then you're not necessarily going to be getting a good result or an interesting result. So you do have to think about random numbers. The other reason random numbers are your friend is while you are developing a software system, often you need some data for that software system to work on, but you don't have the data ready yet, or you don't have access to the data, or the portion of the software that's supposed to read in the data to you isn't been built yet. Random numbers, random data, very helpful. How sensitive are your outputs to your inputs? If they're not that sensitive, it may not be very interesting to have them serve as an experimental variable. Okay, so classical experimental design is full factor here. And again, you take your variables and you arbitrarily assign a high value and arbitrarily assign a low value. Now, I'm saying arbitrarily, but you also want to convince yourself, either through analysis or through experience or through screening, that the high and the low are large enough apart to actually make a difference. Obviously, if you did high and low that were really close together and they didn't make any difference, that's not very interesting. So, high and low. And what this person is showing in this chart with the pluses and minuses, all of the minuses are saying, look, you've got variable one on run one, you've got factor one, variable one at the low, factor two is at a low, factor three is at a low, right? So everything with the negatives is low, everything with the positives is high. And then because there are three factors here, each can be low and high, we get 2 to the third total possible runs or total possible configurations. And that's why he's got run 1 through 8, because you've got 8 possible configurations. So he's doing a full factorial design here. As an example. Then he starts asking these questions of, oh, wait, the main effect in factor 2 is defined as the average difference in response when this factor moves from its negative to its plus level. So we're looking down here, R1 minus R2 plus R3 plus R4 minus R divided by 4. Well, what's happening there? Well, if you look at factor 2, what do we got?
It's signifies the positive and negative.
Yeah, well, every time I want to see where it flips, right? Yeah, every time it's negative, every time it's low, you put the negative value in there. Every time it's high, you put the positive value in there. And then because everything is paired up, high to low, then that's why you're dividing by 4 instead of by 8. It's a simple way to combine that stuff. Now here, the next one is asking, what if there's some kind of interaction between two of these things? And the simple answer, or a way to ask that question here is, he says something that's interesting, a little bit confusing here. You multiply the columns like signs, but really what he's doing is he's doing the old math. Negative times a negative is a positive, positive times a negative is a negative, right? So that's what he's getting here. So if you look at, let's see if I can get it on the same. There we go. Which is he looking at? Factors 2 and factors 1 and 3. So factors 1 and 3, there we go. Factors 1 and 3 are both low for run 1. So negative times a negative is a positive, it's positive R1. And then 1 and 3 are different for run 2. So he's subtracting for R2. Do that all across the board. And again, dividing by 4 because you're interested in that pairing. So I want to just present this paper and those two techniques as ways that you can try to analyze the results. I think most of us are familiar with the first form where we're going to look at, oh, here's all the places where factor 2 was high. Here's all the places where factor 2 was low. Let's average all the high results, average all the low results, and compare the two. Right? That's the intuitive way to do that. Whoops. Okay. I wanted to get into this guy, Latin hypercube, real quick. So this is a little bit of a tougher paper to read. But in terms of experimental design, the previous paper was using the full factorial design in order to give you some examples, but there were only 3 variables. So I'm trying to get to where I want to be in here. No, I don't see it. But But that's not necessarily what you're going to have. You may have more variables than that. So how do you handle that? There's a couple ways to do that. One is we talked about blocking, where you hold one set still and then you modify the others. And that way, since you've reduced the number of variables that you're interested in, you can do a full factorial suite within that smaller grouping. Another version, though, I don't know why I can't find it, Latin hypercube, and you can Google it, the Latin hypercube. It's effectively you're creating random sequences of these things and creating enough runs where you are getting good coverage. So you're convincing yourself that you're getting sufficient coverage of the highs and lows of the different variables without getting the full factorial design. And then from there, you do you can do some of the combining that we just saw to figure out what are the effects of the variables high and low individually and pairwise. This is a paper. When did this paper come out? A long time ago. We wrote this in the 2005. In this paper, we were doing the opera problem, and what we were studying was, hey, let's say you have some ability to learn in a particular scenario, then you take that learned behavior to another scenario. Did the learned behavior transfer, or do you have to relearn new behaviors for the new environment? And again, it was simulation to simulation, so it's kind of hard to say. And one of the reasons we did this is because it was very frustrating when people are doing robots and they're doing learned behavior with robots in a simulated environment, and then they took that robot that learned some behavior in a simulated environment and put it into a real world environment. Typically the robot would just perform miserably. This is 20 years ago though. so guess what? Nobody published those results because nobody publishes when their robot fails, which is bad because that was actually useful information, right? Something happened there that other people could learn from. So we did this, and again, this was simulation to simulation because we didn't have the ability to have a swarm of real robots at the time. No Bobots 20 years ago. Yeah. So what we came up with was these different kinds of scenarios, the door problem, the original upper problem with the doorway, then with a hallway, then with the bent hallway, and we threw different things in there. And the part I want to get to was, been a while since I looked at this thing, the experimental setup. So we set up the environment, and then we had population, right? So here were the parameters: population, sensor range, opening width, and social structure. So sensor range was high and low. Opening width, we had arbitrary high and low. Social structure was on and off. And from there, we could construct these different scenarios. And then to get the results, we were doing pairwise results. So for sensor range high, we paired it with opening width high, opening width low, social structure high, social structure low, and then tried to figure out what the effect of just the sensor range high was. But that's a simple example of again, this is on your Canvas page if you want to read the whole thing, a simple example of an experiment design. And we didn't care about the physics of the machine, so they were all massless points, right? They could have discontinuous turns, things like that. And what they were doing, these simple UAVs were learning how to navigate without hitting each other. So it was a machine learning exercise. But again, the thing was, if you learned in one environment, where would you, and then you transferred to a new environment, would things still work? Right? And I can't remember the results. So there's a picture of what that looked like. And that little circle is basically their sensing radius. And I forget what the results were. That's not important. I want to show you what the design looked like. Okay. So that's all we need for today. Alex, I'm going to talk to people one-on-one about their papers now. So I'm going to stop the recording. And if you want to drop off, you can. And if you want to send me your work, I can review it over the weekend. Okay.